Whoa. All right, so my name is Jerome Mertz. I'm in the biomedical engineering department. And so what we do is we build microscopes. We develop microscopes for biologists. We try to tailor our microscopes to biologists' needs, and the problem with biologists is that they're very demanding. They always want to, it's always the same thing. They want to see more stuff, they want to see it faster, they want to see more, get greater sensitivity. So we've been trying to address these needs, and one solution that keeps percolating in our lab is basically to be adaptive. You don't just look at your sample with the microscope, but tune your microscope to the sample itself. Adapt it to the sample. Oh, yeah, I should have, okay. There we go. So, for example, one example is two-photon microscopy, which you see at the top. Is there a laser pointer? Yes. Two-photon microscopy, what is it? It's a fluorescence microscopy. Basically, you send a laser beam into a sample, get an image. These are neurons inside brain tissue. The problem is, what you see is this, with a regular two-photon microscope. You see these two neuron bodies. You don't see anything else because it's too weak. It's too weak. If you turned up your laser power, well, this would start saturating. So you basically have a problem of dynamic range. What can you do? You can adapt your microscope. In other words, as you're scanning this laser focus, you can change the laser power so that you only deliver laser power where and when you need it, and you go from this to this. We've just increased our dynamic range by 16,000 in this particular example, and it's a pretty good deal. This little electronic add-on costs $500 compared to this $500,000 instrument. Here's another example. This is just regular wide field microscopy. So it's not two-photon. You just bathe your sample with illumination light from a lamp. And what you see is the problem with regular microscopes is they're looking at a particular focal plane. So it's not volumetric imaging. You only see what's in focus. So how can you get volumetric imaging? What you could do is scan really fast with very fast focus scanning mechanism. The problem is then, and it's faster than the camera. So in a single shot, you get all this information from the volume. But the problem is that information, that in-focus information, is swamped by out-of-focus contributions, by out-of-focus background. What can you do? You can adapt your microscope. You can basically, as you're scanning the focus, you can deliver light that's patterned to your sample. So you're only delivering light where and when you need it. And you get this very high contrast volumetric information, again, in a single shot. And it's scalable. What's nice is we can see very large volumes, 1.3 millimeters in size. Color corresponds to depth here. And what you're seeing here is a mouse that's thinking. As these neurons light up, that means that the neurons are active. And here the fluorescent indicators are actually inside the neural bodies. Here they're pretty much spread outside the neural bodies, so it's a lot more diffuse. We're going, again, 30 hertz. Volumetric imaging over more than 1.3 millimeters, which is really hard to do. But this is a way to do it.
You're done?
I'm done. So the solution is be adaptive.